Morning, everybody. We're going to do a quick review of chapter 23 to 25, and then I'm going to go through some examples that will be similar to what we'll have on the test on Tuesday. So let's get right to it. So I wanted to talk quickly about some differences that we're seeing in modeling means versus modeling proportions. So chapter 23 to 25 was all about means. The previous chapters, when we were doing inference for confidence intervals and for hypothesis tests, were for proportions. So make sure that you're aware of the assumptions and conditions. The assumptions and conditions for means will be random, independent, less than 10% of the population, and then the nearly normal condition. So if it's below 15, you really need to make sure that it's unimodal and as symmetric as it can be. If it's between 15 and 30 or 40, you want to make sure that it is just unimodal and roughly symmetric. And then if it's greater than 40, it's large enough that we can use the normal model. But you do just want to make sure that there's no extreme skewing. Okay. So one of the first things about means is that we do not know the standard deviation in most cases. They will usually give us a sample standard deviation. So that's the first thing. Also, always for means, use the t sample. Okay. So on your calculator, you're actually going to see a z sample. Don't use it. Always use the t for means. Always use the z proportion. Okay. They're basically just saying, just make sure you know your differences. The thing that looks like a cursive O is actually a sigma, a small sigma. So you use that for population. I remember the O, population. It looks like an O, population. Then we have standard deviation. That's going to be from that's going to be from the data. And then we have the standard error. Okay, so just remember all different three things. Okay, normal distributions and t distributions, in case it came up as a question on the free response, it could happen. T models are fatter tails, and the lower degrees of freedom make it have a fatter tail. So there is a whole family of T models, one model for each degree of freedom. We already talked about that. Degrees of freedom for one sample t-tests are going to be n-1. For two sample, there's a more advanced calculation that you'll let the calculator do for you. And then we know the formula for t is going to be y bar minus mu over the standard error. And remember, standard error is going to be the standard deviation over the square root of n. Then we have our confidence intervals, and finally pairing. When we do pairings, we have three types of calculations we're going to be doing. We have one sample, we have two sample, and we have pairing. When the difference between pairing and two sample is two sample are going to be two completely independent groups. Pairing is going to be the same group or persons that are going to be doing analysis on. Main ones are going to be before and after. Exercise routines, diet routines, preparing for a test. I'm sure you all, if you took the first SAT, you took it, maybe you did okay, and then you practiced a little bit more and hopefully you did better. That would be a pairing test. Okay, so let's begin and let's go through. I'm going to try and go as quickly as possible through some of the questions I want to make sure we're good on. So the 1960 census results indicated that the age at which American men first married had a mean of 23.3 years. Right? So it's widely suspected that young people today are waiting longer to get married. We want to find out if mean age of first marriage has increased during the last 40 years. So first thing they want us to do is write an appropriate hypothesis. So we're going to make, so we're going to say that our parameter is going to be me write it down. Our parameter is age of male marriage. So our mu here is going to be mu equals 23.3. And our, sorry, what am I doing here? Let me erase this for a second. Let me start over. Our null hypothesis, thank you for anyone who was saying, what are you doing? Our null hypothesis is going to be mu equals 23.3. Our alternative hypothesis is going to be mu is greater than 23.3. They want to know if it's gotten increased. They're going to select 40 random men. Do you think it's necessary assumptions for inference are satisfied? And let's quickly run through them. We have random. The men are independent of each other. 40 is certainly less than 10% of the population of all men. Married men is really what it is, right? And then nearly normal, while we don't have anything showing us it, greater than 40 people, so we can use the normal model. The other thing I can say is we certainly don't know if it's going to be unimodal, but we certainly know there'll be some slight skewing because most men do not get married below a certain age, maybe 16, if that, 18, I don't know. But there'll be lots of men who are getting married much later, their first time. So it's certainly skewed to the right in this case, as we would expect all marriages would be, because you can't be too young to get married. All right, so therefore, use the one sample T. We're doing a test here. Test. Okay. So let's do the test right now. So we're going to plug it. Oh, so we have to figure out what we're testing, right? Let's jump down to question D. The men in our sample married at an average age of 24.2 years. Okay, this is D. 24.2 years. So a standard deviation of 5.3. What is the p-value for this result? And what's our conclusion? We'll do D and we'll do F. So let's jump here. Let's go to stat. Tests. Let's go to the t-test. And we're going to go to stats. We don't have data here. I'm going to put in a mu of 23.3. The X bar they want to do is 24.2. Our standard deviation, sorry, it's hidden here, is 5.3. And number of men was 40. And we want it to be greater than the hypothesis, null hypothesis. Whoa, really? Okay. I didn't think it was that high. Oh, because I put the numbers in wrong. See, I already ran this. And I'm like, wait, what? I put in the numbers wrong, 23.3. So if you get a crazy number like that, you're going to say, what? And then calculate. Sorry about that. Happens to the best of us, but you saw I was confused there for a minute. The number was way too big. So our t-value is 1.07. And our p-value is 0.0145. And we know our degrees of freedom is just going to be 39. So I'm going to write my t. Let's change the color. T is equal to 1.07. Our p-value was 0.145. And our degrees of freedom is going to be 40 minus 1, which is 39. Okay. Let me make sure I got my numbers right. Yes, I did. So my final question is state our conclusion. So our conclusion is because the p-value of 0.045 is greater than the alpha level, which I'll write right now, of 0.05, we fail to reject the null hypothesis. There is no evidence that males are getting married older now versus 40 years ago. Okay, let's write our alpha level right here. Alpha level equals 0.05. Okay. So let's go on to another question now. I'm going to be using some data, so I want to kind of bebop back and forth. Students checked 6 bags of Doritos, very small sample, marked with the net weights of 28.3 grams. So the bag itself said the net weight was 28.3 grams. They carefully weighed the contents of each bag, recording the following weights. Here they are. Do the data satisfy the assumptions for inference? Explain. Find the mean and standard deviation of the weights. Create a 95% confidence interval, and then comment on the company's stated weight. Okay, so let's do these. So let's go through before we do the assumptions. Obviously, random. They picked some random bags, I guess. If they bought them all from the same place, maybe that's a concern. Bags are independent of each other, most likely. Doritos makes millions and millions of bags of these every day, probably. And then less than 10%, certainly. The nearly normal is going to be our concern. So let's go to stat. Let's go to edit, and let's go and clear out L1. Let's put in our data. Clear. 29.2, 28.5, 28.7, 28.9, 29.1, and 29.5. Okay, so now I'm going to go to stat plot, and I want to look at the graph. So I'm going to go stat plot. It's on, and I'm going to go to L1, second L1, and then I'm going to go to graph. I'm going to go to zoom 9 is what I'm going to do. And this happened before. Interesting. I'm going to change my window a little bit. There's really no reason why it starts at 28.5. It ends at 29.5, right? Was that the last one? 29.5? 29.5. Let's do an increments of 0.5. Maybe that'll be too big. I don't know. Let's see. Too big. So window 28.5, 29.5, let's maybe do by 0.3. I don't know. I'm trying to get it to look as symmetric and as unimodal as possible. All right, that's a little better. It's going off the edge because my, what's happening here? Did I miss something? 28.5 is the smallest number. 29.5. You know what I'm going to do? I'm going to do 29.6 because it's falling off the graph is what's happening. Okay, so I'm not seeing it unimodal. Let me see if I can change one more thing. They had 0.25. What if we did 0.4, kind of somewhere in the middle? I don't know. It's just going to make a difference. Probably won't. Yeah. Interesting. It actually did. So let me change my window. So you can see that I'm kind of playing around a little bit with the numbers. Let me change this to max of 4 so I can see the graph. Okay. So what would I do? I would draw this out. Give a quick little sketch of it. So here is my sketch. Okay. And I would talk about being random, and I would talk about this nearly normal. So when I'm going to talk about the nearly normal, I'm going to say nearly normal, it's unimodal, and roughly symmetric. If by chance the graph was not symmetric, you just want to have a discussion of the fact that it's a small number, and we could probably say that with a larger sample, we probably would get it to be more symmetric or something like that. It would be a concern, but it's a small sample. I guess I didn't want to spend a lot of money on the chips. Mean and standard deviations. Now let's go to stat, calc, 1var stat, L1. And we're going to get the mean and the standard deviation. The mean is 28.98 and the standard deviation is 0.36. So the mean, I'm going to come down here. For B, the mean is 28, what was it, 28 point, 0.98. And the standard deviation, SX, is 0.36. Okay, create a 95% confidence interval for the mean weight. So now let's go here. And now we're going to do a 1 sample T interval. So we're going to go down and we're going to do a T interval. Okay. I'm using stats. I'm using data, sorry. Let me go here. Though interesting, I don't know if you saw, it actually pulled in the data for me, but I'm going to go here anyway and just do this. L1, confidence interval is 95%, and calculate. And I get 28.6 to 29.36. So 28.6 to 29.36. Okay. Comment. Okay. Explain in context what your interval means. Let's do D because this is important. We are 95% confident that the true mean weight of the chips is between 28.6 ounces and 29.36 ounces. Comment on the company's stated weight of 28.3 grams. What would you say about that? The company says each bag has 28.3 ounces, but our confidence interval did not contain 28.3. So it seems the company is filling the bags with more chip weight, which is good for the consumer. Okay. All right. So next question. Let's look at this. I just want to jump through the assumptions and conditions on it and go through this. So we have here, don't worry about this as there's a previous exercise. They were calling people about whether they saw and remembered ads. And we have violent programs, sexual programs, I guess, whatever, and neutral programs. And they have a mean number of brands they recalled and the standard deviation. And they asked tons of people, 100 people for each different type. Is there a significant difference in viewers' abilities to remember brands advertised in the show versus violent and neutral content? The assumptions and conditions are going to be the same: random, independent, nearly normal. If it's over 40, you can say it's a large enough sample, so nearly normal applies. And we need to, in this case, the other assumption and condition we have is independent groups, which we would have to take into account. We'd say that each group was watching different shows. They are not related to each other at all. Okay. Is there a significant difference in the viewers? So let's do this. Let's call violent U1, and let's call, we're doing neutral, right? We're doing neutral is going to be mu2. Okay. So is there a significant difference? So let's run through the null hypothesis real quick. So our null hypothesis is going to be mu1 is equal to mu2. And you know what? I see that the neutral is greater than the violent. So I'm actually going to switch these, and hopefully everyone sees why. I want my number to be positive. It doesn't matter. The number would be negative. You just need to have a conversation about it being negative. I don't want you guys to be confused as why it's negative. Is it different? They're asking for difference. So, and this is significant. That's how I knew it was a test. All right. So the alternative hypothesis is going to be mu2 is not equal to mu1. Okay. We already did our assumptions and conditions. Let's do an alpha level of 0.05. And let's do we're going to do, I'll write it. We'll do a 2 sample t-test. Okay. So let's go to our calculator. Let's go to stat tests, and we're going to go to a two sample t-test, which is number 4. Don't worry about number 3. We're not going to use it. Almost like mark it off your page. We're going to do stats, and I'm going to put in my data. So the neutral was 4.65. The standard deviation was 1.62. The number was 103. The violent was 3.02. The standard deviation was 1.61. And quit. What happened? Must have hit enter by mistake. Didn't mean to. Sorry. 4. Okay. And 1.61. Number was 101. And we're looking for not equal to. And remember, we talked about not pooling. We're not going to pool. Okay? No, no, no. And calculate. So we get a t value of 7.2 and a p value that is to the negative 11 power. Really, really small. Not to the power, to the scientific notation. And our degrees of freedom was 202. So let me write these things down. Mrs. J, do I have to write all those zeros? No, you don't have to. The t value, the t was 7, right? That's really high. That's really high. That would be 7 standard deviations away. The p value was practically almost 0. I'm fine with you writing that. The AP people will be fine too. And the degrees of freedom was 202. I wrote the alpha level. Is there a significant? Is there difference? Because the p value of almost 0 is less than the alpha level of 0.05, we reject the null hypothesis. There is strong evidence, okay? There is strong evidence that the viewers of neutral shows recall ads better than violent shows. Question B here was wanted you to compare neutral versus sexual, I think. Let me see. Sexual versus neutral. Let's just keep it violent. I just want to show you how that graph would look. So let's go right to the confidence interval. Let's go to tests, and let's go to a 2 sample t interval, which in this case is 0. I'm going to still use my data, my stats. So I'm going to go there. I'm going to just do a 95% confidence and no pooling and calculate. And the data comes up with 1.18 to 2.07. Let me write that down. So I'm doing B, but I'm tweaking it a little bit. B is going to be neutral and violent, okay? In the interest of time, violent. Okay. So our thing was 1.18. Oopsie. 2.07, I think it was. Let me see. Okay, so 2.08. Okay, so what are we going to say here? We're going to say we are 95% confident that the true mean difference between recalling neutral ads while watching neutral shows versus violent shows is between 1.18 and 2.08 for ads recalled. The true mean difference between recalling ads while watching neutral shows for violent shows is between 1.18 and 2.08 more ads recalled. Okay, Good. So final question real quick about pairing, and then we'll be done, is we're talking about a car having regular versus premium, and maybe you have never thought about it, but supposedly premium is actually better for your car. Some cars only require it. I know when I had a fancy car, which I don't anymore, it required premium gas, and so it was really annoying because I had to pay a lot more money for gas. But you can also put premium in regular cars, and supposedly it'll run better. I don't know if it's true or not. And that we're going to see right now. Is there evidence that cars get significantly better fuel economy with premium gas? This, looking at it, is a before and after. We have cars, all different cars, different people on the street, randomly picked, whatever, and they secretly gave them regular, and then they secretly gave them premium, and they wanted to see the miles per gallon on each of the cars. So let's go through and just do the assumptions and conditions will be the same. There'll be one additional assumption and condition, and that's going to be that it is paired data. And I would write something like car is before and after, something like that, with type of gas. Okay. I would just tell them why I know it's paired data. You have to tell the reader that it's paired data. That's the additional assumption condition. Random, independent, independent of each other, obviously. There's no independent groups because in this case, it's all one. Less than 10% of the population, and you would want the graph to be nearly normal as well. So let's go through and let's plug in the data. Stat, edit. Let's clear out L1, L2. And if you recall with this one, what I need to do is I need to go and I need to have a third column, which is going to then allow me to do the difference. And that's how we do the paired test. 19, 22, 24. I'm going to take a moment at the end to make sure I type them in right because I don't want to have them wrong. And I didn't. So let's see here. Okay. 19, 22, 24, another 24, 225s, 226, 28, and 32. And let me make sure. 16, 20, 21, 22, 23, 22, 27, 25, 27, 28. Okay, so my third column is going to be the difference. Now I can see that it's better gas mileage. I can see in general, I think, in the premium versus the regular. So I'm going to do L2 minus L1. It's not a big deal if you flip it. And who knows, I'm actually not sure if I'm doing it right because I can see sometimes it went down a little bit. So I don't want to assume that, but I can see more of them are on the higher end, and we think that premium should do better, right? And I'm going to hit enter. And now in L3, it's doing the difference between them. A paired t-test is just a t-test, but they're going to do it only on the difference. So what I'm going to do is I'm going to go to stat, tests, and I'm going to go to t-test. And I'm going to do the t-test. The one thing I did not do is I did not do a null hypothesis. So let's do the null hypothesis. This case, the mu d, the mu difference. I'm saying that there is no difference. So that's going to be equals 0. And then we're saying, is there a difference? Is there evidence it gets significantly better fuel mileage? So it's going to be null hypothesis, alternative hypothesis is going to be the difference, mu difference, is greater than 0. Okay, so let's go and we'll do an alpha level of 0.05. Okay, and I'll write it down, we're doing a paired t-test. You've got to write that down. Do not write anything other than paired t-test for this test. Okay, so let's do this. I'm going to go to data this time, and I'm going to do the mu O. It's going to be equals 0, and I'm going to do L3. I'm going to the third data set, and I want to know that it is greater than, and calculate. Okay, so we get a t-value of 4.5 and a p-value. So let me write this down. So the t-value, t equals 4.5. It's pretty big. P-value was equal to point, what did I see there? To the negative 4, 7. So we'll go over 1, 2, 3, 7. Okay. And the degrees of freedom in this case is going to be the number that 10 minus 1, which is 9. Okay. So because p-value of 0.0007 is less than alpha level of 0.05, we reject null hypothesis. Luckily, strong evidence that the premium gas gives better gas mileage than regular. And luckily that's the case because we wouldn't really want to spend all that money if it did not. You guys have a great day. Good luck on your test on Tuesday, and we will have office hours today and tomorrow if you need to. Have a good day. Bye.